Today we are going to discuss Latin square designs, their ANOVA tables, and an example of a Latin square application. The Latin square design was named for the fact that it can be shown as a square with Latin letters corresponding to the treatments. They allow us to control the variation when there is more than one factor being examined. The squares are composed of three parts: the treatments and the two blocking factors. Looking at the Latin square in the bottom left, we see that the treatments make up the 16 squares denoted by A, B, C, and D, and the two blocking factors are represented by the rows and columns. It is important to note that each treatment can only occur once in each row and once in each column, because this is what allows us to control the variance. In addition, while Latin squares can be any size, they work best when they're at least a 4x4, because any smaller reduces the degree of freedom too much. When setting up our Latin square, we must randomize every piece. This is done by first randomly selecting a standardized square, then randomly permuting the columns, rows, and then treatments. The ANOVA table for the Latin square design is a bit different than the typical ANOVA tables, such as a randomized block design ANOVA table. Let's take a closer look at this. The tables are different because they need to consider the sum of squares, degrees of freedom, and mean squares for each of the columns, rows, and treatments, since they do not interact. The first value we take is the degree of freedom, which is calculated using the P-1 formula. Then we find SS, sum of square differences from the mean. These values can then be used to find variance and standard deviation. Next, we calculate the mean squared. Now that we've gone over the basics of Latin squares, let's look at an example problem. Here's our problem. Quality engineers at an aerospace company want to test the protection provided by 4 different casings. The casings will be tested by being thrown in different directions with varying speeds, then analyzed to determine the amount of damage to the casing. Our treatments are going to be the casings, which are spherical, rectangular, a cube, or an egg shape. The columns will coordinate with the directions, and the rows will represent the speeds. Our end result will look like this. I hope this example helped you better understand